In our previous video, we looked at how to calculate the Pearson product moment correlation. We looked at the formula if you ever wanted to calculate it by hand, and then we looked at how to find it in Excel and find it in Python. Well, in this particular video, let's look at hypothesis tests based on correlation. So let's look at a new data set. Here we have a data set. I'll just pull it up in Excel, make it bigger so we can see it. So here we're looking at the relationship between height and weight of girls. So we want to know, is there a relationship between height and weight? In our previous video, we found correlation for other data sets like this one. So I'll give you a moment and see if you can create both the scatter plot and the Pearson product moment correlation. Let's first do them in Excel. So how do we go about doing that? Well, what we're going to do is highlight our data, insert, create a scatter plot. And we can actually make this a little bit easier to see. We can right click on the bottom here and format axes, and you get this display here. If you are in the Windows version of Excel, you also had a plus sign at the top of right of your chart, and that would have brought you to the same little menu display here. And what we can do is we can change the minimum, and let's make this minimum instead say 4 so that it shifts it so there's not so much empty space. We could do the same thing if you wanted to, right click and do format axes and change the other one to have a minimum, let's say 40, if you want to be able to see the data a bit better. Okay, so if you pushed plus on the Windows version of the chart and you came to the same screen, you would want to make sure that you had clicked on the axes and then the little one here that looks like a little chart. Okay. All right, so now we've cleaned this up a bit. We can give it a label if we wanted to. We could give it titles for the X and Y axis of height and weight to make it match. Notice that whatever is the first column in Excel is what it puts on the X axis. Whatever is the second column is what it puts on the vertical axes. If you are in the full version of Excel, you can go and select data and specify you want different ones to be on different axes. If you are instead in the web browser version of Microsoft 365, then it doesn't allow you to tweak it that way. It'll be whatever is your first column is the one that's on the horizontal, and whatever is the second one will be on the vertical. So just rearrange the order of your columns if you want it to look differently. All right, so here's our data. We're looking at this. It looks like we do have a direct relationship. It's a positive correlation. And then how strong is that relationship? It looks pretty strong. We expect the number to be closer to 1 than it is to 0, and we expect the number to be positive based on this information. So we do equals Pearson, and we highlight one column, comma, the other column, and we get a R that is the sample correlation of 0.77. So as predicted, it's positive, and it is closer to 1 than it is to 0. So we then want to do a hypothesis test. Well, a hypothesis test related to correlation. So, sorry, before we do that, this is the formula for correlation. We saw it in the last video. This top part gives you first the cross product. When you find the average of the cross products, you get what is called covariance. And then on the bottom, what you get is a measure of variability for the X's and a variability of the Y's to get us the overall correlation, which we found here is 0.774. But as noted in the last video, no one's doing this math by hand. All right, so we would get a correlation matrix or an output that we got. Now we want to do a hypothesis test related to correlation. When it comes to a hypothesis test related to correlation, we have the population correlation uses the Greek symbol rho, and the sample correlation is R. So here we have our null hypothesis can be that the population correlation, so if we looked at all girls, all their heights, all their weights, the correlation, the relationship between the greater population's height and weight is 0. No relationship. The alternative would be there is a relationship, so rho is not equal to 0. That is a two-tailed test. Alternatively, you could have it be a one-tailed test, a directional test. Perhaps you think that there is a positive correlation, that the more height, then the more weight, or the more weight, then the more height, whichever way, because it's not causation, it's just a relationship. In which case, if you think that there is a positive relationship, you would use an alternative hypothesis where rho is greater than 0. Because remember, the alternative hypothesis reflects what the researcher thinks is going on. The null hypothesis always contains the equal, and the two hypotheses are mutually exclusive, so what's in one is not in the other, and collectively exhaustive, which means the two options cover everything. So if the alternative hypothesis, if we go with an alternative hypothesis that rho is greater than 0, oops, sorry, wrong symbols here, that rho is greater than 0, then the null hypothesis will be that rho is less than or equal to 0. Okay, so remember our steps for hypothesis testing. We state the null and alternative. We state the level of significance, so maybe we're going with an alpha of 0.05. Other common alphas, you could have 0.01, 0.001. If it's a very small sample, you might go with 0.1, but that's pretty rare. So typically 0.05, 0.01, 0.001, right, are usually the common ones. Assumptions and the test statistic. So we are going to be doing a correlation test. The test statistic is a t-distribution, and the formula for the test statistic is going to be our sample correlation times the square root of n minus 2 divided by the square root of 1 minus r squared. And our degrees of freedom here are n minus 2. So the assumptions that come with this is random sampling. As I've said before, all hypothesis tests, the number one assumption, the first one, is always random sampling, because if your sample doesn't represent your population, you can't make any hypotheses or any inferences about the population because they aren't like each other, so they don't match. The second here is bivariate normality. We have two groups. We are assuming that those two groups, the height info, the weight info, that those are normally distributed. So we're assuming that in the greater population, that if we looked at height, we could find, I don't remember which one was X and which one was Y, but we could find the average. It has an equal number of high numbers and low numbers. The mean, the median, the mode are all matching. And we could find the weight, and it would have the mean, median, and mode being the same, this measure of center, and then have an equal amount in either direction where there's less probability of both extremes. That's what we're saying here in bivariate normality, is that we have two variables, they are both normally distributed in the population. Being there's some measure in the center, low probability of extremes in either directions. So we want to do a test. Let's suppose we want to do a test where we think height and weight are positively correlated. We go with this alternative hypothesis. If instead we were testing whether there was a relationship at all, we would do a two-sided test where the alternative is rho does not equal 0. So if we are doing this one, then our decision rule is that we will reject the null hypothesis if it's two-tailed, if our test statistic is greater than the positive critical value, or, I think I ran out of space here, or the test statistic is less than the negative critical value. Okay. two tails. T, negative T, positive T. And over here, if it's an alpha of 0.05, this would be 0.025 over here and 0.025 over here. If instead we were doing this test, then what we would have is not two-sided, but it is one direction, and it's the greater than side of 0.05. So if it is the two-tailed, we reject the null hypothesis if the test statistic is greater than the critical value positive, or the test statistic is less than the critical value negative. If it's the one-tailed test, where we're looking at whether or not there's a positive correlation, then it's the one-tailed test here, and we would reject the null hypothesis if the test statistic was greater than the critical value. So we're just going on the one end. They are going to have different critical values because one puts all of the error on one side and the other splits the error on two sides. So let's look about doing this test. Okay, let's go into Excel. We have our R. We need, so let's do the two-tailed test. And then we'll just practice, we'll do the one-tailed. You wouldn't do both of them because these tests are now dependent on each other. So you really should pick what does the researcher think is going on. You don't do both, you just do one, based on what it is the researcher wants to know and what it is the organization is going to do with this information. So is this going to help in terms of some policy, in terms of some decision by the organization, in terms of furthering some type of treatment program? You know, why do we ultimately need this information? Okay, so if we're doing a two-tailed test, we need our test statistic and we need our critical value. Okay, now to find the critical value, we're doing our t-distribution, okay? And if we do our t-distribution, remember that it is giving you, we actually need the inverse, t-inverse, there we go. We actually need it to give it the probability of everything that's on the left. So if you are doing a two-tailed test, then everything on the left is not 95%, because you have to consider that there's 2.5 on either side. It's going to be 0.975. Okay, and then degrees of freedom. Well, let's go back. The degrees of freedom for this test is n-2. So then let's go in, and we have 12 girls here. So our n-2 means our degrees of freedom is going to be 10. Okay. So for our two-tailed test, the critical value is going to be 2.28. Alternatively, if we were doing a one-tailed test, we need t-inverse. The probability is going to be 0.95 because we have the 0.05 error on the right side. So everything to the left is 0.95. And we'll have the same degrees of freedom, which is n-2. So our 12 girls minus 2 is going to be 10. So you do get a different critical value depending on if you're doing a two-tailed test or a one-tailed test because of where you're allowing the error to be. Okay, now we need a test statistic. To get our test statistic, we need this formula here. It is R, the correlation in the sample, times the square root of n-2 divided by 1 minus R squared. So let's just do this in pieces. So we have R squared. And so we have 1 minus R squared. And in our formula, it is the square root of 1 minus R squared. That's going to give us the bottom half of the formula. To get the top half of the formula, we have the square root of n-2 times R. So we can take the square root of n-2. Well, n is 12, minus 2 is 10. Okay, so that gives us this part that's right here, and we multiply that times R. Times R. So then our test statistic is going to be our number here, which is r times the square root of n minus 2, divided by this number here, which came from, you'll recall, us taking r squared, 1 minus r squared, and then taking the square root of 1 minus r squared. So our test statistic here is 3.86. Now, if you do a two-tailed test or a one-tailed test, you still get the same test statistic. But our decision-making process is going to be different. So if we are doing a alternative hypothesis where the correlation is not 0, so there is a relationship, we will reject the null hypothesis if the test statistic is greater than the critical value on the positive side or less than if the test statistic is less than the negative critical value on the negative side. So in this case, our test statistic is greater than the critical value, and so we are going to then reject and say that there is a relationship between height and weight in the greater population. In a one-tailed test, we are going to take our test statistic, compare it to our critical value. If r, just to go back here, that was the statement up here, if the critical value is more than the test statistic, then we will reject the null hypothesis. So in this case, test statistic is greater than the critical value. We reject here. Notice that when you do your null hypothesis that they're not equal, then that critical value here is lower. Or sorry, let's take that back. When you're doing a one-directional test, you can reject the null hypothesis with lower numbers. Whereas if you're doing a two-tailed test, then you have to get a greater test statistic to reject the null hypothesis. And that's because you're allowing error, but you're only allowing a certain amount of error in either direction. Okay? And so because of that, a two-tailed test is going to require more of a difference than if it's a one-tailed test. So if you already have this inclination as to where the relationship is, that it might be positive or might be negative, then you're going to be more likely to reject the null hypothesis with the one-tailed test than if you just had an uninformed, I don't know, it's just different, in which case then it's possible that a lower correlation in your sample won't let you then say there is a relationship in the population. So just be aware as you're choosing your methods. All right, so a hypothesis test, we've gone through the process. We have stated our null and alternative. We created our significance level. We then identified the test and the assumptions that go with it. So make sure you don't forget to state the assumptions wherever I put them. Random sampling and bivariate normality. And then create your decision rule, analyze it, and then draw a conclusion. Now, we did all this in Excel. We had to do it all by hand. Let's do this in Excel, or not Excel. Let's do it in Python and have Python do it all for us. In which case, we're not going to compare test statistics and critical values. We're going to compare p-values and alphas. Okay? In which case, this one here will reject the null hypothesis if the p-value is less than alpha divided by 2. And in this case, we would reject the null hypothesis if the p-value is less than alpha. So the only difference between the two tests in terms of making the decision is whether you're cutting alpha in half for the two-tailed. Okay? All right, how do we do that? Well, just quick reminder that you can access, and you can't see this, all right, drstephpowers.github.io/BIA. Go here to get access to the workbooks, supplemental materials. Correlation is where we're working right now. Open it up in GitHub, which is this button right here. Open it up in Google Colab. You're in GitHub already. So open in Google Colab. Don't forget as well, we are using the Stats 3 data set. So click on that, and I'm just going to raise this up. Download it right here to your downloads folder and then dump it into your Excel file. And then just a reminder, not going to go through this every time because I'm sure it's getting old for you. Import pandas as PD. So run this, link your workbook to your Google Drive. Make sure you are logged into your Google account and that you have saved a copy to your drive. Otherwise, you can't run the code or amend the code. And then you want to link to your Google Drive so that you can import the data set. And in fact, in this particular case, we are using the data set that I have located right here, which is the girls data set from Statistics 3. And so for me, I have dumped it into a folder called BIBA Handbook, and inside a folder in that called Appendix. So this command line here uses pandas, that's the PD part, to read an Excel file that's located in this location. And I want to pull just the tab called girls, and I'm going to call this whole data set X3. And then I'm going to have it show me the first 5 rows of the data set X3 by using the command head. So it gives me the girl number, the height, and the weight. Okay. Well, from the previous video, how do we go about doing correlation of this data? How do we go about doing a scatter plot? Well, you'll recall from our previous videos that we will import matplotlib.pyplot as PLT. We need that in order to do our graphing of our scatter plot. And we're going to need to take this data here that tells us how to create this graph. And we're just going to change it because this is the data table called X3. And we want it to be, what is this, height and weight, also from X3. The rest of that code can stay as is. So we then plot it, although I guess I should change the labels to be height and weight. So we have our correctly labeled scatter plot. All right, create this. So here we have that same scatter plot we saw in Excel. And then if you want to find the correlation, then we are going to use the command core, apply it to, well, let's wait a second here. Remember that X3, if we look at X3, X3.head, it had that extra column in it, right? It has girls. So if I do X3 core, and I can do that just like I did previously, right? X2 core here, then what it will do is it will create a 3x3 table because it will show me the correlation with girl, okay? And I don't actually care about that. So if you want that to go away because that's not pretty, do X4 equals X3, and look, it's already recommending to me a process. So here's your AI at work. There is AI built into Google Colab that will help you code. And so every day it seems to be getting better and better at recommending code here. So here it is going to take X3. It's going to get rid of girl by just taking height and weight from X3 and making something called X4. And there we go. So we have our correlation, our Pearson product moment correlation 0.77. Okay. Now that we have this information, we then want to do a correlation test in Excel. Or sorry, what are we doing? How about a correlation test in Python? So to do a correlation test in Python, you're going to need a package called skippy.stats, and you're going to need to import here Pearson R. That is going to do your correlation test, the one we just looked at, with Pearson. And in fact, if I wanted to do a correlation test with the diamonds size and price, I could do Pearson R, and then X2 was the name of the data set, and the 2 variables were size and price. And when I do that, I get a test statistic and I get a p-value. So before we get to the girls and heights, if you're looking at this particular one, We could compare this test statistic to a critical value, or we could compare this p-value to alpha. Notice this p-value is very small, telling us that there is a correlation between size and price. That rho is not equal to 0. Two-tailed test, compared this to 0.025 with a significance level of 0.05. There is a positive relationship here. If we are doing that was a one-tailed test. If we're doing a two-tailed test, back up. Too many words. If we are doing a two-tailed test, we're saying there is a relationship. We don't know what direction it is. We think there is a relationship. So, an alternative hypothesis, rho is not equal to 0. We compare this p-value to 0.025 if the alpha is 0.05. So we take alpha divided by 2, compare it to our p-value. P-value is super small. There is a relationship between size and price. If we already have a feeling that they move the same direction, so our alternative hypothesis is that when size increases, price increases, then we would do the same test that we have here. We have our test statistic. We compare it to a critical value, or we can simply compare our p-value directly to the alpha. Not alpha divided by 2, but to alpha. And here we have a super small p-value. We have an alpha of 0.05. We have a positive relationship. Okay? Test statistic is positive. We have a positive relationship. Okay? What are we doing? Height and weight. All right, so height and weight of the girls. You can do it from the original data set, X3, height and weight. You don't have to do it from this reduced version called X4. You can if you want to. It doesn't matter. Those two columns are in both. So here we're doing Pearson R, and then from table X3, height, and from table X3, weight. We do that. We get a test statistic, 0.77, should look familiar. And we get a p-value of 0.003. So this is telling us that there is a relationship between height and weight. If we were doing our two-tailed test, we reject the null hypothesis if our p-value is less than alpha divided by 2. Well, we go here. This is less than 0.025, so reject the null hypothesis. Alternatively, if we had instead, and remember, you don't do both, just pick one based on what you think and what is valuable to your organization to make decisions. If you thought the relationship was positive, so you already had some clue as to direction, then we would compare our p-value to our alpha. And if p-value was less than 0.05, we'd reject the null hypothesis, which in this case, the p-value is less than 0.05. We reject the null hypothesis. There is a positive relationship. Okay, so we can do our hypothesis testing in Excel if we want to do this test statistic calculation by hand, or we can use statistical packages like Python. There are others, SPSS, SAS, R, in order to do the test as well. Regardless of what method you use, always use your process for hypothesis testing, which is state the null and alternative, state the level of significance, state the test, state the assumptions of the test, state your decision rule. So I'll reject the null hypothesis when, so you know ahead of time, and then do your calculations or have Python do those calculations and then interpret the results. What does that mean? We reject the null hypothesis, then the correlation is greater than 0.